Last question on this paper, question 8, testing a couple of things. We've got polymers at the start, and then we've got equilibria, and then we've got rates. So we're given the structure of propane nitrile, and we've got to draw a section of 2 repeat units for polypropane nitrile. So we're going to break this double bond open and have the bonds either side of the carbon-carbon double bond. So there's one repeat, and we just draw another one joined to that. But don't forget these bonds must extend, and that is telling the examiner that you know that this just continues. Why is this manufacture of polypropane nitrile? Why does it have a 100% atom economy? There are no waste products. So now it turns into a test of your equilibrium knowledge. So we're given this equilibrium here, showing how propane nitrile is manufactured from propene. So you can see I've written up there some numbers of moles here. So we've got 1, 2, 3.5 moles of gas on the left, and we've got 1, 2, 3, 4 moles of gas on the right, just in case they ask us about pressure, as they often do. And the delta H is minus 540, so that means it's exothermic, going in the forwards direction. And we're told the conditions used are 450 Celsius and 2.5 atmospheres, and there's a catalyst present. Describe and explain, using Le Chatelier's principle, the effect on the position of the equilibrium. So is it going to move more forwards or more in reverse if you did the following changes? So temperature above 450. So if we raise the temperature, that's going to favour the endothermic direction, which is the reverse direction, and so this equilibrium will shift to the left. And Le Chatelier's principle says that it's trying to minimise the change, so I would get that in if you can. Pressure above 2.5 atmospheres, so that's an increase in pressure. An increase in pressure will favour the side with the fewest moles. So again, the equilibrium is going to shift to the left to minimise the change. And if you didn't use a catalyst, the rate would drop. But remember, there's 2 reactions going on, forward and reverse. And so the rates will be affected equally. And so therefore the position of the equilibrium wouldn't change. So how have I said that? Without the catalyst, the rate of both forward and reverse reactions are slowed by the same amount, so there is no effect on the position of the equilibrium. Part D is a bit of a maths question. A factory is able to make 11.13 kilos of propane nitrile from 220 moles of propene. Calculate the percentage yield. So let's have a quick look back at the equation. So propene to propane nitrile is a 1:1 ratio. That's going to be important. So you can see there I've written there from the equation, 1 mole of propene makes 1 mole of propane nitrile. So 220 should make 220. So let's work out how many moles of propane nitrile we've actually made. So 11.13 kilos has to be turned into grams. You can see I've done that there. Divide that by the MR, which is 210. Gives us 210 moles. So we were supposed to get 220 moles, but we only got 210. So as a percentage yield, actual over theoretical times 100 comes out at 95.5%. And then the final part of the question, part E, is testing our rates knowledge, and in particular using Boltzmann distribution curves. We've got to use a Boltzmann curve to explain the effect on the rate of increasing the temperature and adding a catalyst. So how have I done this? I've drawn the black curve first, and that's sort of my regular or standard temperature. I've got my labels on the Boltzmann axes, number of particles on the y-axis, energy on the x-axis. And then if I'm going to make a comparison about different temperatures, I'm going to need at least two curves. I've actually drawn three here. So if you lowered the temperature from the black temperature, I know they're asking about increasing, but it won't do us any harm to talk about this anyway. If you lower the temperature, the whole curve shifts to the lower energy side, and so it becomes this shape. Remember, it must start at the origin, and then it asymptotes here. It must never cross the x-axis. Increasing in temperature, the whole curve shifts to the right, to the higher energy, and so it takes this profile, and again asymptotes over here. So, activation energy, we've marked that up there. So why does an increase in temperature increase the rate? Well, it's all to do with the area under the curve after the activation energy. Remember, that's the number of particles with sufficient energy to react because they've got energy greater than or equal to the activation energy. So if we compare the black area to the red area, at the higher temperature, the red area is greater. So there are more particles with enough energy, so there's going to be more successful collisions per second. So how have I phrased that? At higher temperatures, there are more particles with energy greater than the activation energy. This is shown by the larger area under the curve. At lower temperatures, there are fewer particles with energy greater than the activation energy. Therefore, at higher temperatures, there are more collisions per second with energy greater than the activation energy. So the rate increases. And then I've gone and drawn another curve there. You wouldn't need to do that. You could just do it all on the same curve. If you put a catalyst in, the activation energy shifts to the left. So you could draw an extra line there. And you just talk about the area again under the curve. All of the areas at the three temperatures have all increased. And so therefore there'll be more successful collisions per second. Let's see how I've phrased that. So catalysts lower activation energy by providing an alternative route, remember. The curve shows a greater area under the curve with the catalyst, so more particles have energy greater than the activation energy. There are therefore more collisions per second with energy greater than the activation energy, so the rate increases. So how are the marks awarded? Correct drawing of the curve, axes labelled correctly, correct shapes for two different temperatures. I was a bit of a swat there and drew three. You wouldn't need to. The idea that the activation energy is lowered by catalysts, we said that. The rate is faster with a higher temperature and with catalysts. Correctly linking greater area under the curve, idea with higher temperature or catalysts, and make sure you get in more successful collisions per second. So that's that question done. And then this is going back to the mechanism question. I now say to my students, from now on, the hydroxide ion, instead of saying OH minus, which would put the minus sign there, I always tell them to say it's HO minus. And then your curly arrow goes from there.